Thank you all so much for coming to the Interplanetary Virtual Machine Seamless Services for an Open World, Litecoin's User Agency, and Connecting Everything. Now, I'm just curious, sort of audience overlap. Show of hands, how many people were in May Milano's talk, Papers We Love? Okay, so almost everyone. Amazing. So there's actually, and I would say unsurprisingly, my team were huge fans of her work and her team and the whole PACT program as well. But there's definitely some overlap. Luckily, when I was watching her slides, I'm like, oh, luckily I focused on the other aspects. So there's some stuff I'm not going to cover here today that luckily was just covered next door as well. So jumping right in. The dominant strategy in our industry, especially around infrastructure for the past couple decades, so really 20, 30, 40 years, has been to gather a group of users together, build a wall around them, and then defend that moat, right? And this is a perfectly rational thing to do and simplifies complexity up to a certain point. But it does have some trade-offs, right? Talking between these systems now is actually a little bit harder, and it's always point-to-point. Right? It's much harder to compose a bunch of different systems together in a reasonable, rational way. The OSI model and the entire tech stack underlying the internet and especially the web, TCP/IP, HTTP, et cetera, do a really great job of networking computers, but they don't really help you network applications. And this isn't even really that new of an idea, right? The late, great Joe Armstrong talked about this pretty much all through the 2010s about wouldn't it be really great if we could have not just every computer, but every process be able to talk to each other worldwide. To talk about this relatively utopian vision, hi, I'm Brooklyn Zelenka. You can find me anywhere on the internet as Xpeed. I'm the co-founder and CTO at a company called Fission Codes, where we work on protocols and platforms for distributed systems. Programming languages and distributed systems are my jam, so getting to work on distributed programming things is pretty great. And while talking about other people, I also want to shout out to Zishan Lakhani, who's spending much of time running Papers We Love today and tomorrow, so if you see him, give him a big high five. He's done most of the heavy lifting on the Rust reference implementation for IPVM. And if you're into Rust, we have a bunch of Rust propaganda posters here, so come find me after. And a lot of this work, our team is pushing forward a lot of it, but it's also joint work with a number of other teams, including Protocol Labs, Expanso, and a few others as well. So today you want to go and put a service online. And step one, you're going to find a service provider, probably one of them, and register an account and set things up. And for the base layer, where, say, AWS started, this is a really great system, right? They'll provide you all of the standards-based things that you could possibly want. Over time, we've needed more abstraction. And so as we work our way up that abstraction layer, well, there aren't standards for these things anymore. So we end up with a bunch of specialized APIs that they provide for things like serverless computing. And that's great, and they do really wonderful work at scale, right? These are brilliant, brilliant engineers. But if we don't change anything about how we're working, this is the future that we end up in, where our APIs and what we're allowed to express online is limited by whatever they want to provide to us. So if we don't want that to be the only thing in the Litecoin of the future, we might have to find some ways to tilt it off its axis and try some different ways. So today we're going to talk about nothing less than connecting all the world's users and services in a standards-based way. And we sometimes describe this as being like the HTTP of compute, or almost like a TCP/IP for a compute. It's open, interoperable, and everywhere. And whatever we come up with when pursuing this goal, it has to be substantially better than the status quo. It can't be just take something off the shelf that currently exists and just creating an open thing that other people can implement. It has to have actual advantages over running things inside of a certain provider, right? Things today work really well. So what if we took a different approach? What does that get us, and what are the advantages we can lean into with that? We've been working on this for a while. I've had like the basic sketch ideas for this kicking around in my head for about a decade. And when we started Fission 4.5 years ago, we knew we wanted to get to compute, and we looked around. We said, well, we would need a really reliable distributed data layer with things like end-to-end encryption and encryption at rest, and that actually handles data privacy and replication in a sensible way. And actually ended up giving a talk last year, Changeloop, about that. So that's the web native file system. And to underlie both of those, you need a robust auth layer if you want to do this in a production setting, right? So you can have replicated data all you like. If it doesn't come with an auth layer, it's not really going to do you good in to actually do things for real. So the way we got here is completely reasonable, right? And it happened by steps as just a smooth function over the course of literal decades. The internet, or especially the web, is really designed for a world of the early to mid-90s, right? Where you had a beige box that lived under your desk. It wasn't powered on all the time, and it definitely wasn't always connected to the internet, because then you type your phone line. So you would rent somewhere else a relatively powerful box that would do things like manage your email, or you could put photos online, and somebody could be connected all the time for you. But because you're not online all the time, right, you need to make these connections. It makes sense then to multi-tenant this and scale it out. But now you're multi-tenant, so you need an access control layer so that not everybody else can read your email too. And as those get more powerful, you stick these behind a load balancer, and you have to scale this out as well. And now you have to scale out your, you move to a more stateless compute layer with a stateful auth and data replication layer behind it. And that's actually a lot of things to manage on your own. So we put it behind an abstraction, and we call that the cloud. And we take the cloud really for granted these days. And that wasn't the case 10 years ago, right? Before I became a programmer, I worked as an Apple genius, and people would come in all the time freaked out, like, where exactly is my data, right? Well, it's in the cloud. Well, where exactly? Well, kind of roughly in this data center, right? And we don't really get those questions anymore. We've agreed that this is a good way of working. But it's not something that has always existed, right? And as time goes on, we want to abstract away even more things. And so now we are moving into this era of serverless, or at least we have the promise of moving into serverless, which is in some ways more cloud than the cloud. It's like almost the pure expression of cloud computing. And so it was this way for many years. And both as a consequence of this and as a result, we try to look at the world as having a single source of truth. There is the database, right? At least abstractly. It's a very client-server world, right? All the compute happens over there. It happens in US East 2. To learn how to be a programmer, assuming that AI is not going to take all of our jobs, right? You have to learn front-end, back-end, Docker, Kubernetes, all of these things, right? It is a multi-year endeavor to become productive, really, as an engineer. And we've developed things like the LAMP stack along the way to be opinionated about how things should work. And then we want to extend that as far as possible by literally shipping the LAMP stack as if it was a single machine into the cloud. And at some point, taking this metaphor and stretching it so far, it eventually will break, right? So the question is, at what point is that, and what comes after? We are taking a random walk through the potential design space. And it's not that we can just look around and see like, oh, there's a peak there and a peak there and a valley there, right? We're performing gradient descent on what is even possible. We are in a local maxima right now, and things are pretty good. It's scary to think, well, if I lose these tools, I'm going to end up in this horrible dystopia. But there are definitely, I have to believe, better ways of working, because this can't be the ultimate in how programming will ever work, right? Things that have absolutely blown my mind in the past few years are fully homomorphic encryption, so being able to compute over totally encrypted data without knowing what's in there, and zero-knowledge proofs, getting a proof back that something was run correctly. And if you told me 10 years ago that that was even possible, I wouldn't have believed you. The hard part here is that, like how everything has happened previously, we still need to have a smooth function in between to say, how do we bring everything else along with us and have a nice pattern in finding the new higher peaks? A good example of this is WebAssembly, right? It's uncontroversial to say that WebAssembly is going to be a very major part of programming in the future, right? But today, the tooling's really not that great. It's getting better at a very rapid pace, but we have to go down this hill a little bit before we can find this next higher peak. Another way of thinking about this is, what if we take all the things that we have today, which are very robust and very like actually a really great experience, pull them apart, look at them, reorient them, and put them back in a new way, right? So instead of saying, what are the parts that we just have now, look at them separately and say, where do we want to get to? And how do I have to orient these things so that I can put them back together in an interesting way? Burning it all down is really intellectually interesting, but it doesn't get us there, right? If something is absolutely perfect from a technical perspective, but nobody adopts it because it's too foreign, it's not going to work. So we're in a new environment now. We're not on dial-up. We have a very different computing world. All of the old stuff is still there, right? The underpinnings of the internet, TCP/IP, is still there. I can send a message from Winnipeg to Saskatoon directly and dial any machine that plugs into the network. But this isn't how people write things. They will put it in a data center, and the closest one in this case would, if we're lucky, somebody will have deployed it in US West, and it has to make this long round trip. And that's fine for an email, right, where it's a couple hundred milliseconds extra. But that is a lot of extra time, energy, carbon, and maintenance on that network, right? We're no longer just dialing machine to machine anymore. So the location of data centers starts to really matter. I'm going to pick on AWS a little bit because they're the major player, right? Here's AWS's data centers globally. And you can see kind of regionally how it's distributed, right? It's mainly North America, Europe, and East Asia. And that makes sense, right? This is where you're going to make most of your money. And it also means that you don't have to invest the hundreds of millions of dollars putting data centers in places that are completely uninhabited, right? So there's a lot of people in those places. And if you want to talk, often the argument that comes up at this point is like, well, what about economy of scale, right? Like there's a lot of, there's high density on, say in Europe, right? Well, there's 50 million people just in this circle, which is about how many people we have per data center in North America. In South America, it's 1 per roughly 500 million. And in Africa, it's about 1.5 billion people per data center. And the one they have in Cape Town is, I'm not sure if it's the most expensive, but it's up there to host data in or to run compute on, which makes sense, right? The overall infrastructure, they have rolling brownouts and, they don't have the economy of scale of having a bunch of data centers nearby and supply chains, all these things. But you're still leaving behind a huge number of people who are online. This also leads to a situation known as data gravity, right? We put a lot of data, and we're producing data at these huge, huge rates now, right? We have geospatial data coming off of cars, VR and AR data, training sets for AI. And we're putting them at a specific location and then putting compute right next to it and then computing over that data and generating even more data that we store there, right? And we're producing it at such a rate and in such high volume that it is actually impractical for us to move that data around in a lot of cases. On the far other extreme, there's increasing demand for low latency computing. So Ericsson, I'm simplifying a little bit here, but the rough line Ericsson draws is 8 milliseconds for low latency computing, which is relatively abstract. So let's put that in sort of back of the napkin estimates here. So in an ideal vacuum, just a photon, not even a packet, no replication, none of this stuff, no failover, would get you from about St. Louis to Havana. To round trip that, so just to even hear back, yep, I got it, you would have to only go out to about New York. And if you do that in fiber, because light travels slower in fiber, that gets you about to Detroit. Which means between the speed at which we need to access data and the volumes that we're producing it, we get trapped in these causal islands. Literally, the speed of light is too slow, right? And yes, you can wait for, for a signal to be able to propagate out far enough and long enough. But again, the amount of bandwidth is just staggeringly expensive for the amount of data that we're producing. And this doesn't get us to use cases like mixed reality or self-driving cars or factory automation. One solution to this is to say, well, I'm just going to work, I know I need to gather data between North America and Europe, so I'll put a data center in the middle of the Atlantic here, St. John's or something. And there are systems that work like this, right? Google has a deployment looks similar to this, and it works pretty well like most of the time when you know exactly where the data lives and you control the entire system end to end? What if we want to deploy things to end users, right? What if they move around and they go to conferences and they still need to access their data and they still want things to run at an appropriate rate? They can't take all of their light cones and overlap them and say, I'm just going to work in this little section here, right? That light cone is moving around all the time. Chris Micklejohn has this really great paper where I think he really captures succinctly this problem. More about data than about compute, but I think it applies here. And that going forward, it is completely impractical for us to have a single or small number of distributed data centers as the primary site for all global information. We have to move towards a picture of the world where there isn't a single place for everything. Because now we have a very heterogeneous network. It's no longer beige boxes. We have very powerful browsers with actually pretty good APIs these days. The phones that everybody's carrying around with them, extremely powerful. Anybody who has a M-series processor in their laptop, these things are just absolutely scream, right? These are great. And cloud and edge and commons networks, things like accessing data over BitTorrent for when we download our Linux ISOs, right? And a single request needs to be able to seamlessly work in between these, right? So it might literally go from a browser to some WebAssembly to an edge agent into a commons network and back. So in summary, places are not a really great way to organize computation, right? Even historically, at Strangeloop, Rich Hickey gave a talk a couple years ago where he basically tears into place-oriented programming as a bad way of working, right? And we're now really hitting those limits. So we're going to take things apart and think about how we can reorient them again. Let's get back to our roots. The Web Foundation said that the internet was built on, or at least the web, was built on 5 principles. Decentralization, i.e. was designed to be resilient to nuclear attack, right? Non-discrimination, bottom-up design, universality, and consensus. So not Raft or Paxos, consensus of standards. And I think we actually nailed this for the host layers. We did a really great job. By IP address, I can dial into any system that's not sitting behind a NAT, right? But we need to take this up through the rest of the stack as well. And I think in the past couple of years in particular, we've become aware, sort of in the zeitgeist, that that enabling user agency is also a good thing. So it's not just those who are capable of hosting, but also end users as well. So we need to empower users to be able to participate, give them the option to move service providers or leave, have control over your data so that somebody can't just drive by and train their LLM on your data, and provide capacity to other people. You should also be able to be a service provider very simply, just by installing some software. Jay Graber, the CEO at Blue Sky, has this article that tries to make an argument for using Web3 as a term as a, sort of a big tent version, but we'll just say self-certifying web, where things like Git or IPFS or magnet links in BitTorrent, where you can get data and route data and confirm that you have the right thing by its hash, right? If we both have a Git hash, we're pretty sure that we're looking at the same thing, right? And to have guaranteed provenance as well. So using public key infrastructure, PKI, to sign where the data came from. So especially in an era where it's very, very cheap now to produce content, to say, no, this actually came from a source that I trust and that I understand. So that's both, often people talk about things like Merkle trees, and that's self-authenticating data structures, but we also need self-authorizing data structures. So let's talk about that authorization bit. So this is the actual underpinning at the bottom of IPVM. Most people are familiar with access control lists. And just as a quick refresher, you have a user and some service that they want to access. And when you make the request, it gets stopped by essentially a bouncer who says, hey, are you on the list? And you present your ID, and they go, yep, cool, you're on the list. I will forward that on to the service. And this is actually really great in some ways, right? Because we've broken things up into 3 stages that are very distinct, and we can plop this in the middle sort of arbitrarily, right? The downside is that these two are not in control, right? The bouncer's in control, and the bouncer can both be buggy or somebody can get into your system, change that. But really, the core issue that we can't get away from is that it's based on rules that live in a particular location. I don't know if anybody else has tried to write access control logic for, especially as things get more flexible, so on something to underpin GraphQL, let's say. It gets really hairy really fast. And now you also have to replicate that around and actually make sure that it's consistent across everywhere you go. Capabilities are having a bit of a renaissance right now. And they work a little bit differently. So you have an agent and a service, and the agent knows how to find that service. And when they make the request, they include a ticket. So instead of being like a bouncer, it's like getting a ticket to the movies. They don't care who you are. They care that you have the ticket stub and says you're allowed into theater 3, right? And if I can't go, I could give the ticket to Zishan, and he could go instead. So we have delegation as well. So now the access control isn't handled in a single location, in a single place. It's the connections between things in the network itself. It puts the agent and the service in control directly. It's stateless because all the required info is in that ticket, works offline, works under network partition, etc. We can make, this is where the movie theater breaks down a little bit, you can make copies of your tickets and hand them out to other people, and even scope that down to say, you know what, you're not allowed to access all of my photos or hand those off to the service. You can just do that with the vacation photos, right? Things like that. And this has a very simplifying effect on how we do auth between services. So OAuth, probably the most commonly used auth system today, breaks into 2 phases. There's basically a setup phase where you register, application asks the user, who registers with the authorization server, and goes back and forth and gets a token, and then goes to actually use it. And the coordination, again, goes through the authorization server, who's the one that's fundamentally in control. And it's, whatever, 10 or 12 steps. If we get rid of this one piece in here, we can radically simplify this picture and make it work between any systems, because you don't have to now go to that single central list anymore, right? So this is UCAN. There happened to be it happens to be the one that's under IPVM. There's a whole bunch of these, ZCAP, OCAPN. There's several. But that same setup and use is now delegation and invocation, which now gives us a firm grounding under which to do open services. Any service that can call any other securely with secure information flow, which is that disorderly programming thing that I've been promised working in distributed systems for a while, right? Where I should be able to tie together any arbitrary services that implement some base interface, right? And this isn't some new idea, right? These are old ideas going back literal decades that are now just being rediscovered because we're getting to the point where we actually have serious use cases for them. I think what we actually want out of computing is what we get out of something like a browser or out of the SDK for your mobile phone. And that is, I want to run some compute, and I want to dip down into the underlying substrate of compute that is there. And I don't care who runs it for me, as long as they're trustworthy. I should be able to just make requests and get results back, regardless of where I'm calling it from, and regardless of who's doing the running, right? I don't want to have to think about where or who. So let's actually get into this magical compute substrate. We're making the bet that WASM is going to eat the world, right? It runs everywhere today. It's in browsers, it's on mobile, it's in servers. And yes, as I mentioned earlier, it's still relatively early, right? A lot of the standards are still being developed, but they're coming along at such a pace, and the tooling is improving at such a rate that it seems inevitable that this will be if not the dominant way to run compute, it'll be very common, not too long from now. With this, we're able to fill out that picture that I gave earlier, auth, data, and compute. And these can all move around and execute everywhere. So having a capabilities-based system at the bottom, having a robust data layer with security and permissions in it, so in this case, web native file system, but kind of pick whichever is your favorite, and WebAssembly with a little bit of extra magic glue in it, so that's the Homestar logo there. And together, this forms the basis for IPVM. Moving data around It's sort of old hat, but same with moving code around. And this is an extension of a very old idea, right, going back at least to the 50s. It says, your code is also data. And your WebAssembly blob is also data. So if we can move things around and confirm that they're the right thing by their hash, well, we can then take that WASM and its arguments and hash link them and have a guarantee that what the job that I'm looking at and the job you're looking at are the same. And now it doesn't matter where it's moving around. We can confirm that this is the right thing to run. We also attach to that a little bit of scheduling information and config. Maybe you want to add a timeout, right? Things like that. And this task altogether is a little bit like a closure, right? You have a function that then says, when you run this, I want you to do this thing. But while you have a reference to it, you can pass that reference around without it being executed. And when you want it to actually run, you put the braces on it, and it actually goes. In our case, the invocation is wrapping it with a signature and actually saying, my intention is to run this thing, basically. And so there's a specific format that goes around that. When this finishes, we then get a receipt that points, again, by hash, to this original task so that we have no confusion about what we ran, any values that came out of it, so pure values, and any effects. Okay? So anything that we want to on-queue back into the system next. Because in this first step, the purple section, we've made an agreement with somebody, hey, you're going to run this for me, and nothing else. And so now, if we want anything else run, we're saying, hey, as a result of that, I want you to on-queue these new things. Plus a little bit of metadata and trace info. To make this slightly less abstract, here's a couple of the fields, the important fields that I was just showing on the last slide. Here's how they're actually shown. You just need a URI, some message that you're running on it, so in this case, wasm run, and whatever inputs it has. This can be any URI, so it could be HTTP, magnet link, doesn't really matter. We bake them down, when possible, into a hash, so hence the IPFS scheme there. So this is a WASM module. We're asserting WASM run on it, and the function, because a module might have multiple functions, add 1 and 42 as the argument. But maybe you don't want to wait around, and maybe you don't know which all of the arguments that you want to run yet. So maybe you're waiting for something else to finish. Well, I don't want to have to wait for that to go across, all the way down to Australia, run, come back, and then I can issue the next thing. I want to say, hey, await this other task, and its output, pipe into here for me. And so we can do distributed promises directly with hash linking. That gives us something that looks like, or in fact is, data flow. So we have tasks, and they can await on each other, so they're piping data into each other as they go, and they can both fork or join. That's all fine. And from a programming perspective, these are all broken down into granular tasks, and that gives the scheduler, the distributed scheduler, the ability to put these on whichever machines make sense. So when we have data gravity and you need to compute over a petabyte of data, you're not going to push that over the network. We're going to try to push as close to possible, if not right on the machine, the job that needs to run on that data. Right? And so by taking out the questions of where exactly is this going to run, we can give the machine, the scheduler, the freedom to make good choices about how things will run in the moment. So maybe it decides, hey, these two should run on the same machine, and those second two should run on the same machine. As long as they're outputting receipts and they can pass those around, this picture continues to work, and it respects the semantics that the programmer expected. Matchmaking, so I've talked a lot about WASM. And WASM is really the easy case, especially when you make it pure and deterministic, right? You can put WASM into a deterministic mode. But what if there's other things you want to run? You want to run a CUDA job with a GPU. Well, we don't want people to have to PR into every implementation of this thing. It's just a base routing layer, just like how the internet works, right? It doesn't care about the specific application as long as the sender and receiver understand what they're talking about. And so it can do matchmaking and do routing between the two. The upshot of this is that while you can still call into very high availability services, right? You can still go to AWS or Azure, where people are working very, very hard to do very high availability things. Well, you can also have lower availability things that are very close to you, right? Maybe somebody's sitting next to you with a GPU, right? And now you have multiple options. You can always fail back into the high availability service when the nearer, less reliable thing fails. Or even say, hey, you know, I want to make sure that this is definitely going to happen. I'm going to send the job to 3, and we'll get results back from all of them, and I'll basically race them. And because now anybody can be both a service provider as well as a requester, that means that there's a higher degree of availability. And when you take, especially geographically distributed, low availability machines and you plug them together, you get actually really high availability if you take that as an abstract thing. So we sometimes joke around that, you know, if enough people run this, we get infinite nines for WASM. So there's always the chance that you'll be under a network partition, that you're the only node that can run it, you know, et cetera. But it helps solve these things by working together as a commons, as opposed to a single service provider. Serializing between each step is really inefficient, as you can imagine. So we don't want to issue receipts in the main thread, right? So we're using the WebAssembly component model, which is still, you know, still in flux, still not finalized. But it lets you take a bunch of different modules and stick them together and just have a really efficient, you know, single program. And then we pipe out, right? We tee out asynchronously where that boundary would be, and let an async process turn that into a receipt if it needs to go over the network, right? And so then we can turn it back into this network-friendly format. The advantage of having receipts like this as well is that if somebody has you know, a different workflow, and then they happen to hit a section that there's a receipt for, they can skip that and just pipe that receipt directly in and keep going. And so they can skip steps as well. They can memoize, basically, at global scale. When we replicate out like this, what we normally want, right, is as you add more machines, you add more parallelization, you want to have linear scaling, right? Typically, that doesn't happen, right? There's coordination overhead, you know, data contention, all these things, right? Dropped packets, retries, you know, so on and so forth. And in fact, it can get really, really bad, especially if you're waiting on another process or another machine, or the network's gone down, or all these things, right? It can actually end up degrading performance, having a huge, huge number of machines as well. But when you're working in a deterministic, highly replicatable system, and if you believe that there's a power law on a lot of people will be interested in running these things and, you know, fewer things as a long tail, then you can get global adaptive optimization, which is, you know, by analogy, like, say, BitTorrent, where, again, you're downloading your Linux ISOs, and a lot of people are really into NixOS, you'll get it really fast from people near you, right? You can just pull those receipts out of the network and skip the computation completely. Some people have been calling this run once and run never again. So it works like a reverse lookup table. You can do AI moderation and tagging, and that can be a relatively heavy thing. You know, you want to do tagging on an entire movie. Maybe that's going to take, you know, some minutes to run. Okay, somebody's already run it for you. Or maybe several people have run it, and you can compare that the receipts match. Now you don't have to run that too. You can do validation on large numbers of signatures. You can build transitive trust networks and do things like thumbnails and cropping. So as people ask for things in certain sizes, especially as, you know, new phones come out and they have, you know, slightly different aspect ratios, et cetera, the first person who does that can register it into the system, and now nobody else has to do the crop again. Here's a little demo that Zishan put together. We actually have a slightly prettier one now, but I think this one's clearer. So here's a cat on a keyboard in space, obviously. It's actually quite a large image. And here's two workflows represented in JSON. We normally do this in CBOR for efficiency, but just to make it a little bit more legible. And the two workflows overlap the first two steps. And so we're going to run the first one. And this actually goes out to the network and, you know, does the crop, and we get, you know, something back. Great. And then we're going to rotate. And then we're going to simulate a down node by quitting the process. And the blur times out. We start the process back up again. And it doesn't have to recompute the crop and the rotate. We still have those receipts around. So we now have a crash-oblivious workflow automatically. And even if somebody else had run those, they would be able to grab those out of the network as well. And same thing for workflow 2. We don't have to redo that work again. We can just pull those out directly because they're memoized. And we get the grayscale. So the more people running things, especially the popular parts of this, speeds up computation for everyone. One of the challenges that comes up immediately is trust. So there's a trilemma. It's Juan's triangle after Juan Benet from Protocol Labs. You can maximize performance if you trade off verifiability and privacy. And so if you have a service provider, you can absolutely use that in the system, right? Or maybe you're going to run it yourself. You're saying, oh, I'm on a low-powered phone. I want this to run on my desktop at home, right? Great. You can do that, and you trust who's running it. But in the general case, you probably want some level of verification. So because these are deterministic and we're getting receipts out at every step, well, we can either run the entire workflow again or spot check. Depending on how paranoid you are, maybe you even want to have it run multiple times. And we then just check, did you get the same hash for all the receipts, especially for the last one? And if the answer is no, well, you do a split search on it, and you find where the disagreement ran, and you just check that one step, and then you slash them. So there's an escrowed cache incentive to not do this. Eventually, we think this will move to zero-knowledge proofs. This already exists for WASM. They're ZKP WASM runtimes, but they're a little bit on the slow side today, and they're very, very new. But what that gives you is when they run, you get back a short hash that guarantees you, with very, very high probability, that it was run correctly. And finally, let's talk about safety. So we've talked mainly about deterministic pure things, which is sort of the easy case, right? You can send that out to literally anybody and they'll run it for you, and you can check it automatically in yourself. But we need effects in the system, right? So I think most people are now familiar with pure versus impure functions, where you have an input and an output, and that's just totally pure, and maybe you chain a bunch of these together. And then effects either read or write to the environment around them. And in order to get the safety properties that we want, at least down at the layer of the protocol, so not in the in a DSL or in a programming language, we need to be able to compile down into the ability to split these out into separate steps, so that we can manage them appropriately and get the kinds of consistency that we care about. So it doesn't actually quite work like this, but just as a metaphor to help understand how such a thing would work. Pure functions just go up into a general stream, and literally anybody can run them, right? So you have very, very high availability on this. Queries, so you want to do an HTTP GET or read from a database. Well, you send that off, and it doesn't matter, maybe this gets optimistically run by in a work stealing queue, but accidentally 2 people ran it. It's actually fine, right? We're not changing the world, we're reading from it. And when we receive that back, we turn it into a pure value. And if that value was wrong, we can roll back over it. Otherwise, we can just now treat it as just an assertion, hey, this is the value that came out of the database. And if somebody wants to rerun over this whole thing, they can just take it on face value or check, hey, did somebody else verify that too? The hard one, and the one that looks more like how people run compute today, is when you want to mutate the outside world. So you want to send an email. That has exact once semantics. You don't want on retries for that to run 7 times, right? So you need to get a lock on that process and actually find this specific machine is going to do the thing, receive back the receipt, and then unlock the process. And that can't be rerun, right? It has exact once semantics. But everything to the left of that has really nice properties. They're essentially transactional, right? We can rerun the whole thing. If something crashes, we can reuse things, we can rerun them. It's totally fine. We can replicate them, et cetera. The 3 properties that we actually care about for this are mutability, idempotence, and determinism. And that means that we can mix queries and pure computation pretty much arbitrarily, as long as mutation goes at the very end. If we try to intermix it, then we have to deal with partial failure, right? Which is a hard thing for a lot of people to wrap their heads around when coming into distributed systems, right? It's like, well, I got halfway through, it failed. well, now you need to roll back some state, all these things. It gets really tricky very quickly. Some of the research coming out of Microsoft, and especially this Ambrosia paper, makes a very convincing argument that if we can phrase computation as something that looks like a database transaction, we get all the transactional stuff for free. And we can separate all these failure conditions that we normally have to fight with in distributed systems away from the programmer completely. They can program in something that feels way closer to writing on a local system. So to simplify that a little bit, as long as queries and computation interleave, that's totally fine. But mutation, super scary, has to go at the end. Also, by having data flow in the system, it means that we don't have guarantees, or the programmer doesn't have a guarantee about, other than the dependencies on the data that's coming in, the scheduler can reorder this to say, okay, well, mutation shouldn't run super early in the flow. We should push this to the very end. And now that's safe to run. To wrap up, we've built this all spec first, so on top of a bunch of reusable and remixable specs. In fact, people are now taking these things and using them for all kinds of stuff, asserting data in DHTs, checking signature verification, all of this stuff. And so if you don't like any of these parts, swap something else in. That's totally fine. You want to reuse it? Great. And otherwise, please get involved. And you can find it at that QR code right there. Thanks.